Hi there, I'm Haleigh.
And I'm Jonny.
And you're listening to Jonny, Haleigh, Day of Fun.
Fun. Who do we have on today?
I don't know. Let's dive in and find out. Welcome, everyone, to another episode of the Day of Fun podcast with me and Jonny. We are joined again by our friend, Dr. Joe. Hello, Dr. Joe, our astrophysicist friend. So glad
Hello.
you're here again.
Thank you. Thank you for having me. I'm very happy to be here.
Yeah, it's great having you.
Thanks.
We are super excited, and I want to just dive right in and ask you to tell me what happens if our sun explodes, because I've been thinking about it and I've got some silly ideas for some sci-fi stories, and I need to know how out in the ether I am or how in the factual world I am.
Okay, cool. So do you want me to give you the good news first?
Ooh, I don't know, Jonny. Do we want good news or bad news first?
I don't know. Patting your stomach, kind of speaking.
Yeah. Let's give us a little padding. We'll start with the good news for padding.
So it's unlikely that the sun will explode, since it's not the type of star that will. So we're safe, unless there's some extremely intelligent alien species out there that wants to do something with the sun and cause it to explode.
Yeah.
Well, if they're that intelligent, they'll probably be like, "Why would we do that? Don't destroy that beautiful planet they have going."
Exactly.
Right.
So let's magically cause the sun to explode.
Okay.
Right.
And it's destroyed completely. And 8 minutes later, we would find out about that.
8 minutes later, we would find out. I mean, at least news travels fast in our star system, right?
Yep. So, let's say it doesn't explode. Let's say I snap my fingers and make it disappear, right? We won't know that it's gone for 8 minutes. Because by then, and then we'll see, that there's no light or heat anymore, and that will be catastrophic pretty quickly. But on that same time scale, right? If I magically remove the sun from the solar system, there's no mass in the middle, and so 8 minutes later for Earth, we start flying straight off into space.
Just nothing's tethering us anymore. We're just out there for all of it.
Yep, that's right. Now, of course, that. Mercury would go first, and then Venus, and then after Earth, all the other planets. But we would, continue orbiting until about 8 minutes later, because gravitons, the modulators of gravity travel the speed of light, and so it would take 8 minutes, and then we would go off tangentially on our orbit into the Milky Way.
Is this something that are there scenarios like this in other star systems that have been observed or that we are aware of that are out in the cosmos?
Not observed, although we do have an interesting observation of a star encounter where we suspect things might have happened if there were any planets in that system. We don't know whether there are or not, but we've seen the two stars pass very close to each other, and so you would expect gravitational effects. But we can do this, in simulations with a computer, and gravity is pretty well known, and so our simulations are pretty high fidelity. So we can do all sorts of different scenarios like this.
Is there any? Oh, sorry. Go ahead.
I was going to ask you, to your point of the light going away after let's say the sun disappears 8 minutes later, then the light disappears and we start to lose our gravitational pull and start to drift. I was going to ask, would we start to drift technically before the light would disappear? Like, how would that work? And when the light disappears, would it be just gone, or would it like dim like a light bulb?
Well, so the light and the gravity effects are going to be at the same time.
Okay.
It depends in our magical realm if we slowly make the sun disappear. But let's say I snap my fingers and it's gone completely. The last photons that left immediately before I snap my fingers take 8 minutes to arrive, and then that's it. So it would be instantaneous.
So I mean, our moon starts flying away, and so our ocean tides just go bonkers, right? I mean,
the moon may not fly away. I mean, it's affected by the sun, right? But it's in orbit around the Earth, and so it would probably continue with us. Now, it might change orbit because the sun, does impart a gravitational impact on the moon.
I was going to say, how sweet of the moon. Thanks, Bestie, for sticking with us in the dark times. We appreciate you.
And it would be dark and cold almost immediately. Did you experience the solar eclipse last week?
I didn't.
I did
I
not.
didn't do the drive to go see everything or whatnot, but I was doing the checking out the pictures and stuff. It was very overcast where I'm at that day, so we didn't have a whole lot of opportunity to go check that out.
So the reason I bring that up is when an eclipse is more than 50% or so, and it gets maximum, whether it's total or up to about 50%, the drop in temperature is remarkable and noticeable and very rapid. And so, without the sun, that would be even more rapid and,
dropped into
worse.
Like instant ice age kind of thing.
We'd have some, I mean, the surface is still warm and the atmosphere is warm. There's a blanket, but yeah, it would be
very
bad very quickly. Yes, exactly.
You're gonna notice.
Yep.
Well, what's that movie? Is it The Day After Tomorrow, where they're running away from the freeze or whatever? It would be kind of like that.
Yes. It may not be like that, but
trying to shove wood into a fire to stay alive.
Yeah, exactly.
Oh my gosh, so interesting. But the other one was if it was a black hole, because that's the sci-fi story that I want to write. Is a planet that's like slowly being pulled into a black hole and it's inhabited, which so how far outside of any sort of reality is that? Am I into sci-fi fantasy, right?
Where you have a planet orbiting a black hole. So let's, before I answer that, let's continue with our magic.
Let's continue. Yes.
And instead of making the sun disappear, let's turn it into a black hole.
Mm-hmm.
And so the good news is that the sun can't turn into a black hole given its mass.
Good news for us. Yay.
But magic too, I'm snapping my fingers, and now the sun is a black hole. Again, 8 minutes later, we'll see that there's no light, but the mass of the sun is there in the black hole, right? So we will continue to orbit the black hole.
Okay.
At exactly the same orbit, because magically I turned one mass of the sun into a black hole that has a mass of the sun. So the gravity is there.
The gravity is there. The light and the heat source is no longer there.
That's correct. Yes.
Okay.
So now we're not a rogue planet floating off into space. We're continuing to orbit the former sun that is now a sun black hole.
Okay, so this is fun for me because in my little sci-fi idea, like I am, my character is tending to bioluminescent plants that have developed on a planet that is like slowly being sucked into a black hole, right? So in my mind, I'm kind of like, is there evolutionarily enough time, if such a thing could happen, for those things, for like bioluminescent plants to develop on a planet to create its own light, and could that also then develop like human intelligent life, right? I mean, obviously, again, this is just fun sci-fi speculation for me, but how long would that planet perceivably have to, before it gets sucked into the black hole, into the event horizon and is gone forever? Does it have time to evolve and develop bioluminescent plants and sentient life?
So here's the fun thing, and the answer is that you can tweak that to suit your purposes, right? So the bottom line is, magically turning the sun into a black hole. So the event horizon of a one solar mass black hole, a black hole that has the mass of the sun, is 4 miles in radius, so 8 miles in diameter. So very small, right? But it has the mass of the sun. So you would need to be really close to the event horizon before you got sucked in.
So really, you would be able to just be orbiting this black hole.
Yes.
The way that so I can tweak it, and in theory, it would work. Like this planet just orbits a black hole, and we have our own light on the planet. I like it. I can make this fit for my little story. Hooray!
So that works. Now, how do we? So in our solar system, with the magical black hole now in the center, not even Mercury would be attracted to the black hole. It's too far away. Remember, I mean, it's a little 8 mile diameter thing in the middle of the solar system. So that's nothing astronomically. Okay, so now if you want to heat things up and your planet is orbiting, you need to have it lose energy in some way, because if it loses energy, then its orbit gets smaller. and it'll get closer.
Okay.
So you could have it, I mean, how might we do that? We could have, you know, another star passing nearby, causing it to change its orbit gravitationally, or you could have the solar system going through like a dense cloud of gas and dust, and
I was
that
going to
dense
say
cloud
like comet, or because like Earth goes through the torrid meteor stream, right? Like twice a year.
Yeah.
So is there potentiality? I mean, where's the good news in that? Where's our potential for being smacked by a big bunch of comet debris and knocked out of our orbit kind of thing?
Well, that's probably, I mean, you'd need to be pretty big to do that. So a comet would have effects on the surface, but probably not change the orbit. But if
Okay.
you know, if the solar system or that stellar system happened into a dense region of star formation or something, there's, you know, maybe more material and bigger chunks of, you know, dead planets or whatever, or stars. And so in that way, you could have an encounter that causes it to lose energy and start spiraling into the center of the system.
Okay.
So that makes it interesting.
So that's where your like first act, like big issue is, right? Like I like it.
Yeah.
See,
could
look
be.
at you'd be great for a consultant on like a film script situation, 100%.
Right.
As
No,
long as
sorry,
I'm
go
not
ahead.
sucked into it, right?
Yeah, as long as you
Yeah.
don't get sucked into the black hole, it's fine.
I was gonna ask you, like to her question of like you being hit by like an asteroid or whatever and being like bumped out of orbit or whatever. Don't we, as Earth, don't we have like a lot of I guess you could say a debris field around Earth at the moment that kind of shields us from asteroids? Like because we get hit by asteroids quite often, but not enough to really impact, you know, life as it is.
Not
So
not
does
recently, right?
well, yeah, not
Right.
recently,
Not recently.
for sure,
Yeah.
for sure. But is that true? There's like a debris field or something like that that kind of shields us in a way?
Well, I think certainly our atmosphere shields us to some extent,
Yeah.
right? Because stuff burns up. You know, if it's too big,
Mhm.
it would survive, you know, burning through the atmosphere. I don't think there's a shield of debris. I think,
Okay.
and I mean, there might have been in the early solar system, right? Because
Yeah.
you know, there's a disk of material that's, you know, orbiting in the solar system out of which the planets form. And then probably around every forming planet, there was a disk where moons and other things formed. So that
Mhm.
might have protected us, although
Okay.
that disk of material is made up of, you know, rocky chunks of all sorts of
Yeah.
different sizes. And if something plows through that, it could cause more to fall into the Earth.
Mhm.
I think what's protecting, if you want to say that, it's not really protecting us. It's just that the number of objects that might crash into the Earth are far fewer than they were, you know, when
Yeah.
the Earth was forming. And so it's a numbers game, and that's you know why we've been relatively lucky at the moment. But
Yeah.
but it'll happen in the future, and
For sure.
you know
And
it'll be
like
good.
Because there's stuff
yeah,
flying
and
around out there.
yeah, and I'm guessing size has a lot to do with it too, because most of it burns up and then some gets the, you know.
Yeah, absolutely.
Yeah.
So not only size, but also composition. So if it's a big fluffy
Okay.
snowball, right? You
Yeah.
know, that might a bigger one of those is going to burn up preferentially compared to a same thing that's the same size that's made out of
Mhm.
iron, right? And so composition is really important as well. And there's stuff out there with all sorts of different makeup.
Yeah.
You know.
Mhm.
Mhm.
So I'm going to shift gears just a little bit because I know
Yeah.
we've talked about dark matter a little bit last time. Like we didn't get in too deep into it,
Mm.
but there's and so I mentioned this to you before. There's in South Dakota where I'm at,
Yep.
like over in the Black Hills area, they have the SURF laboratory, which is like the big underground laboratory. And I know they do a little bit of stuff with studying dark matter there, and they're developing like, or they're digging a new facility underground. So can you explain a little bit about like why the experiments they do with physics and studying things that are out in space, why some of those studies have to be done so deep underground?
Yeah, that's neat, isn't it? That
Yeah, it's like,
you're covering yourself up.
yeah, it's like we got to go under here to understand all the stuff that's way out there. Like,
Mhm.
Yep.
you know, how does that work and why?
So the main question the main response, but the main question is, what are we observing down in this deep former gold mine, right? The Homestake mine.
Yep.
And the answer is subatomic particles or things that are very, very difficult to detect. So one of the experiments they have and or will have is a neutrino detector. And neutrinos are these little particles that come from the fusion process inside of stars and exploding stars, and they hardly interact at all with anything. So you could pass one neutrino through a light year of lead. If you had a lead bar that was 1 light year long, the neutrino would pass through as if there was nothing there.
Okay, interesting.
Trillions of neutrinos pass through our bodies every second, coming from this, mostly from the sun. And
that's exciting.
Without doing anything to, water molecules or anything in our body, they just pass right through. So that makes them very difficult to detect, right? Our detectors are catching these objects, and if they're passing through the detector, you can't easily detect them. But there's so many of them that every once in a while they'll smash into a water molecule in our body or something in the detector, and they can be seen. So the problem is there's all sorts of other noise, right? So there's charged particles coming from space, electrons and protons. There's radioactive particles coming from the Earth, the rocks in the Earth. And these cause noise in the detector. The detectors pick up this stuff as well. So when you go deep underground, you're using all of the Earth above you to shield out all of that stuff, other stuff coming from space that would cause noise in the detector. And so you can, when you get a detection of one of these very weakly interacting particles like a neutrino, you're more confident that it really is a neutrino and not just something else that's causing noise.
Right.
Yeah.
So how are neutrinos then associated with, are they associated with dark matter? Like how does that go together for like what they're studying or trying to understand more about dark matter, since there's obviously not a lot understood about it?
Sure. And so the experiments with neutrinos are to understand neutrinos on their own. Now, interestingly, when dark matter was first discovered in the late 1960s, neutrinos, which were even less known back then, were thought to be one of the candidates for neutrinos because there's so many of them, and we expect so many of them. So if they have a certain amount of mass, there's so many of them, they could make up the dark matter. We're not detecting them easily. They have mass, and so they have influence on matter.
Okay.
Well, we now know, back then, in those days, 55 years ago or whatever, we didn't really know what the mass of the neutrino was, if it even had mass. Now we do, more or less, and they don't have enough mass. So neutrinos are no longer a candidate for dark matter.
So dark matter has more mass than neutrinos.
Yes, or it's yes. And or another way of looking at that is that you have a huge number of neutrinos, but even with that huge number, their mass is too low that when you add it up, it makes the dark matter effect. So dark matter particles could have more mass than neutrinos, or there could just be more of them. And so now switching into detecting what dark matter is, because we still don't know what it is. There is an experiment deep in the old former mine, for the same reason, blocking out natural background noise to try to detect a particle of dark matter. And dark matter is similar to, or we believe it's similar to, or it has to be actually similar to neutrinos, because it's not interacting electromagnetically with anything. And all we can tell, the only reason we know it's there is through mass, its impact and influence on other matter that we can see.
So it's just like dark matter and neutrinos flying about all the time. There's all kind of stuff going on in the quantum realm that we just don't notice all day long, right here in front of our faces.
Yep, absolutely.
So amazing.
And so the current expectation, current theory, I guess, hypothesis is that dark matter is a subatomic particle, but we're not detecting it yet. And there are some indications that, or some thinking that says we should have detected them in particle accelerators and other places, but we're not yet. And so, you know, the jury's still out on whether it truly is a particle or something else. And that's one of the experiments that's running now at SURF is hoping to detect these dark matter particles.
I hope they figure something out, and I hope that one day I can get a tour of that place, even though it's kind of spooky freaky to think that, I mean, you are traveling down an elevator way down under Earth. It's a little bit, I want to see it, but I bet I would probably get a little claustrophobic.
Maybe, but you know, take a look at the instrument halls. They're big, vast spaces, and so
yeah, no, like the facility is amazing, and the things are like, once you're in there, just, you know, you're kind of just in a building with no windows, I guess, right? And if you can kind of suspend disbelief a little bit and not freak yourself out that you're a mile underground, right? You could be okay.
Yes, exactly.
I was going to ask, like, when was this place built or developed? Because I'd never heard of it until Haleigh brought it up.
Oh,
so I'm not. Oh, go ahead, Haleigh.
No, I was gonna say I should know this, but they did essentially convert an old mine into this laboratory facility.
Was it relatively recently, or
20-ish, maybe 18 years ago or so?
Yeah.
Okay.
I was gonna say recent, because the more I age, the more recent becomes a relative term, right?
Right.
And that's the nice thing when you're in the astrophysics realm. You can go all the way back to the Big Bang, and time becomes a much more relative thing, and then you can feel really super young all the time.
Right.
Yes, exactly. And it time both flies and kind of doesn't matter anymore, right?
Yeah, right. I love it. That's the best bit.
So I was going to ask you, Joe, we're going to shift back into this kind of just however you want to answer it. We'll just go with whatever. So if you were going to colonize a planet, which would you pick? And then on top of that, the second part of that question is, what are the top reasons why you could or could not inhabit that planet?
Oh, interesting.
Anywhere in the cosmos.
Anywhere
that we are aware of that there is a planet that could sustain life. Why? What are we? I mean, obviously water and atmosphere, right?
Right.
But
for us, yes, absolutely.
What challenges with Dr. Joe?
Yeah.
Well, at the moment, so you know, we have detected lots of planets around other stars. But at the moment, the vast majority of them are only through gravitational or other indirect means, and so we don't necessarily know. We might know what their mass is, but we don't know any characteristics.
Okay.
You know, based on mass, sometimes one can get density information, and so then you might, you know, realize that it's a rocky body as opposed to a gas giant like Jupiter or whatever. But the vast majority of them, that's about all we can say. Some of them we have a little bit more information, and we can say, yeah, you know, there's probably liquid water, oceans or whatever on this planet, or, you know, no, this one is covered in sulfuric acid or whatever. So it's hard to necessarily pick one of those that are outside of the solar system, an extrasolar planet at the moment. And even if we could, technology now means that we would almost certainly not in our lifetime be able to make it to that planet. So let's stick with the solar system.
Okay.
I was going to say I like warmth, and so that counts out some places, but everywhere that we look is probably pretty cold, right? So if you're looking for something that is most similar to Earth, then Mars has to be where you're wanting to go, just from the, you know, landscape, as it were. It's and something like Mars, solid body, you know, it's going to be easier to land on and to build things. The problems that we encounter in addition to being able to travel there, right, is life support. And so life support is both oxygen, water, food, radiation from space. And by radiation, I don't mean only X-rays and gamma rays in the electromagnetic spectrum, but also high energy charged particles like protons and electrons that are traveling close to the speed of light, that are very, very dangerous, right? So you get
can you explain a little more about that and why that is? Like, why is that different of like on Mars versus on Earth?
Yeah. So on Earth, we have a strong magnetic field that protects us from these charged particles, electrons or protons, either one. Electrons are negatively charged and protons are positively charged. We have a relatively dense atmosphere. It's the magnetic field that protects us from that. The atmosphere protects us from X-rays and gamma rays. They get absorbed in our relatively dense atmosphere. So Mars has a much thinner atmosphere. It has an atmosphere, but it's thinner, and it has maybe a magnetic field, but it's certainly weaker than Earth's. And so these charged particles that are coming from everywhere, but mostly from the sun, because that's the closest source, they're smashing in and smashing into the surface. And X-rays and gamma rays, there may be some absorption. I don't say this definitively because I would have to look into it, but I suspect that there's probably more of them coming into the ground than they do on Earth, where none of them penetrate to the surface. Probably a higher ultraviolet flux from the sun. And so, these are dangers as you're traveling to the planet. But let's put that aside. Let's say that we're able to get to the planet. Then now you have to survive on the surface. So forget about oxygen and water and food. The radiation field is pretty bad. So the nice thing about Mars is that, there's a lot of dust and sand on the surface. And, you could make your structures and then cover them in dust and sand, and that offers some sort of protection. There are also caves on Mars, and so you could build inside of a cave, right? We know that they exist. We've seen them from orbit. So you build inside the cave, and you're protected, just like the.
I was gonna say you gotta get underground and then you'll be okay.
Yes, exactly.
So you might have to have all kinds of the human ant farm situation on Mars.
Right.
Everybody go underground.
Yep, absolutely.
Interesting.
Now, so the question there is, are you going just to colonize and to have another place, but Earth is where it is, or are you looking in the far distant future when the sun is going to end its life and expand as part of that process, causing all sorts of issues for planets like Mercury, Venus, Earth, and Mars? In which case, if you're looking on the long term, of course, that's far enough in the future that we would probably have interstellar travel at that point and we could leave. But if you want to stay in the solar system, maybe you think about going to one of the moons, the icy moons of Jupiter or Saturn. And
that's
so you
an
have
interesting, fun thing, living on a moon. Okay.
Yeah. Well, I was talking to Haleigh about this question too, because it's an interesting question, because each planet is consisted of different material. Like there's some planets that are just gas, there's some planets that are solid ice, you know what I mean? So it's every planet and every surface is going to create its own problems,
Sure. Yeah, and challenges, right? Yep.
Yeah,
absolutely.
for sure.
Absolutely.
Yeah.
Well, now I kind of want to go and live on a moon though, because that's fun.
Well, we kind of live on the icy surface already, so.
Yeah, up where we're at. I mean, we're finally in springtime and there's not snow, but anything can happen in the Dakotas. Let's not bring ourselves a May blizzard, shall
exactly.
we?
Knock on wood, right?
Right.
And then I was going to ask you, since you're a Star Trek fan, I kind of wanted to ask, as far as movies and shows in the sci-fi realm, what movies, or are there things in movies that have kind of inspired scientific research and development, like just an idea of like a cool, or is it kind of the other way around?
And that was something we were talking about a little bit, like even from Star Trek, like are there things from sci-fi TV movies that have made scientists go, oh, maybe that could be, let's go check that out.
It's a very futuristic thing, and back then computers were as big as your house, so it's like
right.
Exactly. So I think the short answer is probably yes, and it probably goes both ways, right? But look, so we're only limited by our creativity, which at times is fantastic, but also is limiting. So go back and look at science fiction from the 60s, or even earlier, of course, but 60s, 70s, even the 80s, where they're talking not about a far distant future where you can basically make up anything, right? But like at 20 or 25 years or even 50 years in the future. And, the time that we're living in now,
Right.
and say, and, it's kind of cute how they've made up these futuristic things that were futuristic for them, and yet are,
that now we have
primitive.
that.
I'm still
Well,
waiting.
I'll come back to that.
Yeah.
Or it's just so still rudimentary that, you look at that and think, oh, that was so silly of them 25
Yeah.
years ago to
Yeah.
think that all we'd have is this. But to your point, Haleigh, so Star Trek, right? Look at all the
Yep.
stuff on Star Trek. The tricorder, right? So I have a device here that can
Yep.
act like a tricorder, and medical imaging devices and medical
Yeah.
diagnostic things that were thought up by Star Trek. And I think that was probably because it's not just a book, right, where you have a limited space that you can describe things. It was a series, and
Yep.
they could explore. But I think they were very far leaning in technology. And whether they had any thought, Gene Roddenberry and the other writers, whether they were thinking, hey, in 50 years, it's likely we're going to have this or not. The reality is that we have a lot of the stuff that Star Trek was foreshadowing. Now, is that because someone was watching Star Trek as a
And
kid
got excited
and said, I'm
and
going
said,
to
Yeah.
Yep.
Yeah.
I'm gonna make that. That
Maybe.
sounds cool.
Yeah.
And so, I don't know definitively, but I would be very
Okay.
surprised if that weren't the case. But I think it's also, that they were being influenced by what was happening around them in the 1960s.
I've always thought it was interesting too, like back in the 60s and so like to your point of like looking into the not so distant future, Back to the Future.
Yeah.
I'm still waiting on my flying skateboard.
Yeah,
So
exactly.
Your hoverboard.
not here yet. Yeah. I'm still waiting.
Yeah.
Well,
But
you've
They
seen
play with
those.
them.
Well, you've seen the drones that they have that they put one on each
Yup.
corner, and they're kind
Yup.
of, so that's
Well, and
almost.
that's interesting.
that is
I
true.
mean,
I never thought of that.
because I've seen too where they do experiments where they use sound vibration to like levitate things, right?
Yes. Yes.
And so like maybe we just need to like integrate some of our like skateboard technology with some banging tunes, and we'll be able to float, and that's how we get it rolling.
Wouldn't that be awesome?
That would be so awesome. I would love that if I had a hoverboard powered by my Spotify playlist. That would be amazing.
Right.
Can we get that rolling? Somebody out there, figure that out.
Yes, that's right. Listen to us and do it. Come on.
Yeah, listen to
Right.
us, come up with the ideas, and then you can, put our faces on your brand. Like, that'll be great. We're here for it. I love it. Okay, so the other thing I wanted to ask, so what things, everybody kind of in general in our human consciousness, we kind of like to focus on the negative and the doom and gloom and the spooky scary. But what things should we be excited or hopeful about when we're looking at what we're studying with astrophysics, with, dark matter, with all these interesting things? What things should we be excited about or hopeful about in what we're able to look at in the stars and on our own planet?
Well, so it's all exciting, right? And
It is
and I
all
think-
exciting.
But people listening to this, watching, could be thinking, well, okay, dark matter is neat, and if we find out what the particle is, that's cool, but who cares, right?
Mhm.
Or black holes are awesome, and that's neat, but they're way out there and they're not impacting us. Who cares, right?
Right.
And that's the kind of question that I don't get often, but you get it occasionally, especially with astronomy,
Mhm.
because astronomy is about looking at the universe and what is the black hole going to do for us. But why are we doing this? Astronomers love fantastic, beautiful things about the universe. We love to understand how the universe works, but it's more than that, because in understanding how the universe works, that allows us to refine our understanding of the laws of nature and models of nature and that sort of thing. And understanding how the laws of nature allow us to do better technology, right? So the work that we're doing in astronomy today may not have an impact on society until 50 or 60 years in the future. But understanding black holes is neat for understanding how they came about. But black holes are nature's laboratories. They're an extreme region in space that we can't reproduce on Earth. And so again, you say, well, who cares? Well, because we can test the laws of nature in the most extreme environment. And if the laws of nature fail there, then we have to go back to the drawing board and tweak our understanding. If the laws of nature are proved in that extreme environment, then we have great confidence that, we understand what's going on. And so it's a little bit of both of these things as astronomers and astrophysicists study the universe. But then that understanding of the basic fundamentals of nature allow us to make better technology and make hoverboards and
all the new energy sources that we could potentially figure out.
Exactly. Yes.
I enjoy this. Absolutely. So the laws of nature, I know we talked a little bit about this last time, and we didn't really get to go necessarily into it, but when you were talking again about dark matter and the younger universe, when you go further out and how things don't, you were saying that there were, planets and galaxies that were bigger than would have been anticipated based on the time that we think they've had. Mm-hmm. So can we go into maybe a little sci-fi, but the concept of time, right? Is it possible that it operates differently? Because our human time on Earth is based on the sun, right? Like we base how we measure time on the sun. But so how is it different as when you're looking into like astrophysics and out into the, again, younger universe? How are astrophysicists measuring time when you look at that? Like, are we still just, our time measurements are all based on human Earth experience time, how we measure it? Or is there another method that you're using when you're talking about, light years or how many billions of years back the younger universe is? Can you talk a little bit about that? Like how time sort of functions in there?
Yeah, a little bit. So perception of time is a human, how do I want to say this? I have to be careful with my words because we're entering a philosophical realm, right? So
yes, we are. But
I think it's safe to say, so our perception of time is a human-centric thing. Mm-hmm. And to your point, it's based on the rotation of the Earth, which gives us the day, the dark light period of the day. We could base it on the orbit of the moon, and gives us longer weeks and months, right? The moons.
Moons, I like it.
So, a second, which is a fraction of a day, is something like a second with some alien civilization, 5,000 light years away. Are they going to have exactly the same time concept? No, probably not. Presumably they in their early days, they were using the orbit of their planet and rotation of their planet to set that. So there's a perception element to it. Now, modern day timekeeping is based on something that's a little bit more natural, which is the frequency of variations in a cesium atom, and so it's based on something fundamental, right? And it doesn't have, it could be whatever. And again, another alien civilization may base it on something else. So if we travel out there and meet the Vulcans, we're going to have two time systems that are off, and we're going to have to try to figure out how to rectify that. But it's just a conversion factor, right?
I was going to say, like keeping train stations on time, right? How are you going to do that? But how are you going to keep the interstellar travel on time schedules if our times are so very different?
Yes, but that's a easy thing to do, relatively easy, right? You just figure out, you set a galactic standard or whatever, right? But now getting to the laws of nature. So do we use different methods for timekeeping? No. We assume that time, whatever that means, is the same in different locations and different periods, different times in the universe. Does it need to be? Maybe not, but if it's not, then we don't know that, then we might have some problems, right? Because there are time factors in many of the laws of nature that we use. And so because of that, so the time that you plug into that equation, that time
Right.
factor is going to be different, again, for different civilizations.
Mm.
But presumably the law of nature that's describing whatever, gravity or whatever, is universal,
Mm-hmm.
right?
Yeah.
So aliens are going to have some sort of other formula, but they're fundamentally the same, right? Again, we need to have some conversion factors to change
But we're
from
measuring the same
Yeah.
phenomena or the
Exactly.
same, if you're looking at me like, Schrodinger's radioactive isotopes, and they're going to
Yes.
take the whatever amount of time to
Mhm.
break down, right? They're going to break
Yep.
down at that rate.
Yep.
And so with the younger universe, then, are there any new developments, or could you talk to us a little bit? Because that fascinates me. Just the idea that, way out there, we think, well, those things shouldn't be as big as they are, or they shouldn't have had this much
Yeah.
time to develop like they have, and yet they have.
Yes.
So, like, what are the theories, or are there theories yet on, well, why is that?
Still, it's early days, so these observations are relatively new, and
Okay.
they're coming in faster because Webb is observing more, and the other observatories are observing more, and now that we've found these things, we're focusing attention on them. So we're getting more and more observations, but it's still early days, and I think the jury's out, if we can say it that way, on exactly what's happening with these big objects.
Okay.
It could be, as in many cases in astronomy, that there's certainly big objects, bigger than we expect at that particular period. And so that's a surprise, but it could be that those big objects are easier to detect. And so,
Okay,
there's
sure.
3 of them, and we've detected 1, and then next year we're going to detect the other 2, and that's it. Everything else is as we've expected, and they just happen to be,
So
the
the anomalies are
Yeah.
easier to spot first, kind of thing.
exactly. Yeah. Well, the anomalies, but certainly the brighter objects are easier to spot first,
Right.
and if you so let's it's not quite the same analogy, but when you look at a beautiful spiral galaxy like our Milky Way,
Mm-hmm.
and you can kind of see our Milky Way behind me here.
Yeah.
But you look
Yeah.
at an exterior galaxy and you see those beautiful spiral arms and things, right? The reason you're seeing those spiral arms is because there is ongoing star formation within the arms, and stars of all different masses are forming. The vast majority of them are like the sun and lower mass, but those are faint.
Mm-hmm.
There's a small fraction that are very big and very bright stars, and they're very bright. And so they trace out the spiral arms where they're being formed, and so we can see those spiral arms. But there's a swarm, far more, thousands, millions of times more stars that are less massive than the sun. It's just that we can't see them. And so, you look at that spiral galaxy and you say, oh, look, we now know what it's composed of. But if you look at it initially, you say, oh, that, spiral galaxies are made up of only massive stars. Well, not really. It's just that, that's the cherry on top of the sundae, and that's the only thing we can see because they're so bright.
Mm-hmm. Kind
Okay.
of
So
is.
maybe that's the case with these early universe objects. I kind of hope not, because it's more interesting to try to explain something that we didn't expect, which we're not able to do even for those that we've discovered yet. That there's still work going on there. But the simple answer could be that they're things that we're detecting now are just a small minority of the the forming galaxies and supermassive black holes at that period. We're gaining more and more information, as the days go by, and so we'll be able to answer that question in all aspects.
I'm so excited. I'm so excited for just one day for Dr. Joe to text me and be like, you won't believe what they've figured out now. And I'll be
Right.
like, Jonny, we got to have a podcast right now. We got to talk to Dr. Joe right now. I can't wait for that to happen.
It happens.
I mean,
And so
if that does happen, please do tell us immediately. And we
Yep.
we might just have to jump right on a podcast so that we can talk about it, because I will be so excited.
No, that's fantastic. And obviously I don't have the crystal ball, but things happen all the time, right?
Yep.
And that are unexpected and or that we expect. So new instruments turning on all the time. We're going to have a fantastic new observatory in a year or so, and
where's that?
That'll be lovely to talk about. It'll be in Chile. It's called the Rubin Observatory.
Ooh,
and
up in the mountains.
I'm sorry.
Oh, way up in the mountains of Chile.
Yeah, it's high in the mountains. But what's new and novel about this telescope is that it's designed to image the entire night sky visible from its location every 4 nights. And so it's observing like on strips, it's taking images, and then every after the the 4th night, then it starts over again and starts imaging. So it's very sensitive to what we call transient objects that brighten on very short timescales, seconds to hours to a few days. And we really don't have much insight into those sorts of things in astronomy because, most of astronomy, we're looking down a very narrow straw, right? And all this other stuff is going on behind us, and we don't see what's happening. But Rubin will, I think, will be game changing. And
that's interesting. So what you're talking about is maybe sort of like flashes or things.
Flashes,
of light that like you don't understand like what that might have been because it's not a big enough snapshot, right, to observe.
Or we've just never seen them. But there are things that we know about, right? So exploding stars, supernovae in other galaxies, asteroids that that we don't know are out there, and they glint for a couple of hours and then they disappear. A few other things that explode and are there for a couple of days and then fade out. So we've seen these sorts of things, and we can expect that. But there's also, I'm sure, there are many more things that we've never seen, but we will be discovering them. So some simulations show between 1 million and 10 million such events per night on the Rubin telescope.
That's a lot.
Okay.
That's amazing.
And again, so some fraction are going to be asteroids, some fraction are going to be supernovae. In that case, it's the volume, because the more we have to study, the better it is.
Right.
But again, it's the things that we had not contemplated at all that are going to be
the exciting things that show up once the process of elimination, all those other things. Like, that's exciting.
So when that turns on, and again, that'll later next year, I think, is the plan.
Okay.
Well, guess what? You're going to have to be coming on to talk to us about that. When they open that thing, we're going to be like, Dr. Joe, we're going to have a celebratory episode.
Yep, that sounds fantastic.
I love it.
So I was thinking of like with the study of the sky and everything like that, or just we just want to look up for some reason. It just intrigued us.
Sure.
But I was gonna ask, this is kind of a 2-part question, because do you think the necessity of studying the sky came from the need for navigation, like a navigational tool in the ancient worlds? And because the Vikings, they would use almost like a quartz to look through overcast sky to find the sun.
Yes.
You know what I mean? Yep. I think they call it just solar stone, but they call it like solocin or something.
Tell me more about that little trick. Can I do that?
Well, the Vikings used 2 navigational tools. They used ravens, and then they used quartz. Well, this quartz, they would, if it was overcast, like we have in our lovely Dakota sky. So if you were on the sea and you couldn't use the sun to navigate, you would hold this quartz up to the sky, and for some reason you could navigate and you could see the sun through the sky, through the quartz. It would like reflect on the quartz, or the UV rays would hit it or something, and it would show you the sun, so you could navigate. And then ravens, they would use ravens just to find land. It was more of a let's get off this boat kind of situation.
Let's get off this boat.
But like, how many? I guess my question is how much of the ancient studies do we still use today? Like, because it seems like they had a really good understanding of the.
Right, like we don't expect that they should have had the understanding they have, and yet you have like megalithic structures that are ancient structures that are obviously were observatories of the stars.
Yep. Because for some reason it all comes to navigation in one way or another.
Navigation and timekeeping.
Yep.
Timekeeping,
which go hand in hand, right? So you need timekeeping to be able to navigate. And so I at a minimum, the strong foundation that the ancient
Yep.
peoples have provided us now,
Mhm.
go into everything that we know. Are we using old techniques? We're using modern versions of some of those old techniques, certainly.
Yep.
But I think more importantly is the understanding of nature and the universe, right? That they passed down and allowed us to and is the foundation of the technology and understanding that we have today. So yeah, timekeeping, and so remember, yeah, we're surprised, right, at this, but at a minimum, remember, no artificial light, right? So it's
Yep.
dark, and it's dark for 12 hours. And so there's a lot of time when you're out there staring at the sky, wondering what's going
Yeah.
on, and you're seeing things that, we either don't see today because of light pollution or because no one looks up, right?
That's the thing that it fascinates me too, the idea that, we have obviously light pollution and our regular pollution and all the things that kind of cloud our atmosphere. Like, what an interesting thing it would be to be able to sort of just plop yourself back like 13,000 years ago and be able to see like because you probably could see a lot more with the naked eye at the time.
Yes.
Right. And so our expectations of their ability to observe things is sort of muddled by the understanding that we have of what we can see with the naked eye currently.
Yes, that's right.
Yeah.
Like,
Put Dr. Joe in a time machine, he'd come back as a god.
yeah.
I can tell you when the eclipse is
Right.
going to happen.
You're
Be
right.
screaming on the top of a mountain.
And I love it. And then suddenly you would be written into all of the religious texts, and it would be like, hey, there's Dr. Joe. We know him.
Hey, we know he was on the podcast last
I know
Right,
that
yeah, there we
guy.
go.
I love it. That's so funny.
Well, on our episodes, I have a wrap-up question. And basically it's because we're in the Dakotas.
Mhm.
So what would be Dr. Joe's Mount Rushmore of science fiction books, movies, or series? If you could say you're going to Mars tomorrow, you can bring 4 of them with you.
Ooh,
What
I
do you
like
bring?
that. You're going to
What are you
Mars
bringing?
tomorrow. What sci-fi, literary,
Mhm.
movies, or TV do you must absolutely have while you are traveling to Mars?
Yep.
Okay, so I need Star Trek. So everything,
right.
all the series and all the movies.
Okay, I'll let you have that.
Well,
Absolutely.
yeah, Star Trek can be its own bubble.
Yep.
Okay.
It's a
There we go.
series.
Forbidden Planet.
Okay.
I don't know. I don't know if I know that one. Forbidden
Oh,
Planet.
that's yes. You'll have to look that. That's a 1959 movie.
Okay.
Okay.
With a very young
Okay.
Leslie Nielsen before he was a comedian.
Before he was Naked Gun.
Okay, cool.
What, Johnny? We need to
Yeah,
watch
we'll have
that.
to check
Yes,
that out.
this
now,
is
for sure.
this is a great, very thoughtful and thought-provoking
Okay.
movie. So
Cool.
it's
That's
one of the
exciting.
classics. And yeah, so look it up, Forbidden Planet. So
For
that's
sure.
2. Oh, how do I limit? I would want Larry Niven's works with me. Can I bring
Larry
multiple?
Nivens? Absolutely.
Yeah.
Yep.
Yeah, Larry.
We'll
I put
say
it
you
on the
can bring
memory
an author's
disc, right?
works.
Yeah, I'm
We'll
gonna
say
put that down. I mean, because listen, this is research for me too.
Right.
Okay.
This is good for me to research for my sci-fi knowledge and writing. Like, let's
Yep,
get in
yep.
there.
If you're not familiar with Larry Niven's universe and body of work, I would strongly encourage you to.
Yeah, I'll check it out for sure.
Yeah, for sure.
It's very rich and very interesting. And then I guess Isaac Asimov. Let's say Isaac Asimov.
All
Okay.
right, fair enough. All right, I love it. I gotta see now. Now I'm gonna
And
have
he's
all
an
kinds of
author
home.
as well.
Yes.
I was
Okay.
gonna say now I'm gonna have to do all kinds of research and dive into all those things. Forbidden
Yeah.
Planet, though, we're definitely gonna have to have a watch party, Johnny. Like, I love this.
Yeah, that sounds very interesting with Leslie Nielsen. I'll
Oh,
check
yeah.
that out.
That's
I
very exciting.
I think you'll like it. It's intriguing.
Okay.
And
Thought-provoking.
very well
Very
done
good.
for the period too. It's
Mhm.
it's a nice little jewel, I think. I think you'll find that too. I hope you do.
Awesome.
Oh, I'm sure. I love it. I'm
Awesome.
excited about it. Well, before
Yeah.
we let you go, though, is there anything you want to share out for folks? Obviously, we'll share your links again in the description, but is there anything you got going on right now or things that you want to direct people to at the moment?
Just nothing to direct at the moment. Just keep an eye out on the sky, and yeah, some new observatories opening up soon. It's a little early yet, and we'll keep you informed. But yeah,
Cool.
just keep up the interest in astronomy. That's all we can ask.
When Ruben opens, we're gonna have an
Yeah.
episode. I'm super excited about it.
Excellent.
I can't wait. Well, thank you so
Yeah,
much
thank
for
you.
joining us again, Dr. Joe. It's such a pleasure to talk to you about the universe.
For sure.
Thank you. I appreciate the interest and thanks for having me. I loved it.
Thank you so much. We will definitely
You're
have
right.
you back again.
It's always great to talk to you.
Nice talking to you.
Hey, thanks so much for listening, y'all. I've been Haleigh.
And I've been Jonny.
And this has been Jonny, Haleigh, Day of Fun. Thanks so much for listening. Check us out on Patreon, patreon.com/JonnyHaleighDOF. And we're JonnyHaleighDOF on Instagram and at gmail.com. Send us your hate mail. We'll read it out loud on the podcast, won't we, Jonny?
For sure.
Awesome. Thanks for listening. Peace out, y'all.
Later.
Special thanks to the Parapost Network for the support of their community. Check out all the great podcasts on the Parapost Network on Facebook.